Welcome to today's webinar titled A Robust Approach to Vision-Based Terrain-Aided Localization, based on a paper published in the spring 2025 issue of Navigation, the Journal of the Institute of Navigation. This paper can be accessed from the Navigation Open Access website at navi.ion.org, where you can read, download, cite, and share this article and many others. Today's webinar is presented by Dan Navon. Dan Navon holds a bachelor's and a master's degree in computer science from the Technion Israel Institute of Technology. He is currently an algorithm researcher at Adasky Limited, where he develops advanced perception algorithms for thermal imaging systems in automotive environments. In his private life, Dan enjoys rock climbing and drumming and is happily married with 2 daughters, Liron and Arbel. Today's webinar is being recorded and will be available on our website, YouTube, and other social media channels. During this presentation, we will accept questions from the audience. You can submit your questions by selecting the Q&A button in your viewer. Now, thank you for joining us. We are going to turn the time over to Dan.
Thank you for introducing me, Beth. Hello, everyone. Welcome to today's webinar on our recently published paper, A Robust Approach to Vision-Based Terrain-Aided Localization. I am Dan Navon from the Technion Israel Institute of Technology, where I conducted this research with my supervisors, Dr. Hector Rothstein and Professor Ehud Rivlin. Today, I will demonstrate a method to overcome the challenge of precise localization without a reliable GPS. Today, I'm currently working at Adasky, where we develop thermal sensing solutions for the automotive industry. And let's start. So what is the problem? Imagine an autonomous vehicle, a said drone, that lost its GPS signal. Now, we can think about many applications where this can happen, as in a search and rescue operation, a package delivery to remote areas, or even emergency supply to disaster areas without reliable satellite coverage. So in this visualization, we see the green dots as the real location of the drone, and the red balloons represent the estimated location by the navigation system. You can see here both spatial error and drift error along the trajectory of the drone. So, given a series of images from this drone, can we, from this approximate location, how can we reduce the true locations? How can we close the gap? So, a bit of background about the structure and the images, about the structure and depth that are inherently ambiguous. So, maybe some of you know the Salar in Bolivia, where people like to take photos that they can play with the structure we've seen. So in this case, we can see both couples standing further from the camera, or maybe a woman that's eaten by her partner. But anyway, in both cases, we see that some peculiar image where we see tiny objects and we cannot fully understand the structure. I mean, by we, I mean the computer, because we have some prior knowledge regarding the size of the people, and we can understand that these are big people that's standing further from the camera. Another example is a soccer ball, which captured roughly the same amount of pixels in both images, but we have some prior knowledge regarding the size of the boy and the palm, so we can understand that this is probably a big soccer ball and this is a tiny one. But a computer or something that computes not necessarily can understand without the semantic information about the object in the scene. So it's hard to understand the structure of the scene using a single camera. That's why we'd like to add another camera. Now, having just a single images before, we cannot tell whether this green sphere is wrapped by an orange ring or whether there are 2 objects. But using the second camera, we can clearly see there are 2 objects in the scene. Moreover, we can tell that this green ball is closer to the camera because of this disparity between the pixels. We see that a long shift in the amount of pixels. So now that we have two images, we can do something called triangulation, which is raycasting through the object, raycasting a ray through the object until it intersects with the ray from the other camera. Now, with this technique, we can find the depth, but it's relative to the camera. Now, it can help us to determine the 3D location, but it highly depends on the baseline. So if we will double the baseline, we will also double the depth. But in this case, projecting the object back to the images will result in the same pixels. So the depth and translation are ambiguous, having no knowledge regarding the baseline. So we would like to solve this somehow, and we would like to use a digital terrain model. Some of you who hike may be familiar with this hiking map, where we see these contours around the mountains, where each contour represents a 10 meters height difference. We have some reference point as 480, and we know that each contour represents 10 meters difference down the mountain. But it's kind of hard for the computer to process this map, although it's an option. So we use a digital terrain model or digital terrain map, which essentially is a function of XY coordinates that outputs the height of these points. And it's easier for us to work. Now, having some digital terrain model and having some 3D unscaled model, if we will be able to match them, and so we can understand the scale of the problem, and hence we can also understand the baseline and where to locate the cameras. And so we would like to do so using ray tracing. And the ray tracing is usually used in computer graphics to calculate the amount of light in each pixel, the color of each pixel from some object. But in our case, we use ray tracing to determine the real-world location of each 2D feature we've detected in our images. So how it works? We send a ray through the 2D feature until it intersects with the DTM. Now, this intersection gives us the actual 3D coordinate of that feature in the real world. However, there's still an important challenge. Sometimes this ray may miss the real object we see in the image. And for example, if we see a cliff, and we might miss it, and because of this initial error in the estimated position, and we can target the wrong mountain. So we will soon see how our algorithm is overcome these mismatches. So let's go into the method. Now I will explain a bit about how we reconstruct the scene. So given a pose P1 and R1, we can see that there is this patch on the ball. This ball represent our digital terrain model. It's just an example, but to understand how our method works. So in this case, we see this black patch on the soccer ball, and the distance is marked with lambda. The intersection point is QT, the true location of this patch in the real world, 3D location. Now, as we said, we have only the estimated pose, P1 and R1, and we model it by some delta P error and delta psi, which is close to the unit matrix, because we assume there is a small change in the rotational error, but we are okay with the high error in the position error. So from this point, we cast a ray with the length of mu until it intersects, and it intersects at point QE, which is the estimated 3D point. Now we assume that both QE and QT lay on the same plane, This is the coplanar assumption, and we test it by multiply distance between them with the normal at QE, just in tests. So we can say that this cross product is equal to 0. Now, previous approaches, I won't go into all the mathematics. It's elaborated in the paper, but and so I will briefly go over past solutions. So they try to solve it by combining both absolute pose and relative pose and constrain it directly to the DTM. But it resulted in nonlinear set of equations, which is costly to compute. So our first innovation is to decouple the problem into first finding the unscaled 3D model, which is the unscaled structure of motion model. And then using ray tracing, we can match it to the digital terrain model. In between these stages, we can find and remove outliers due to the high sensitivity to the solution, which is the second innovation step. I can stop for question. Don't see any. So I will resume to the filter methods. So our first method is scale statistics. As I said, we have some estimation regarding the depth of each feature, an unscaled depth estimation, which we mark as lambda hat, and we computed the ray tracing depth using MIP. So let's take a look on this toy example where we have these hills and mountains in the image, and by looking at the first hill, we are looking from P1 and have some distance, which is lambda, to this hill. But unfortunately, our navigation system thinks it's slightly higher. And when we raycast mu, we hit the mountain behind this hill. So how can we identify this as an outlier? In most cases, we believe that the intersection with the DTM should be matched to the structure of motion model. So we assume that there is a constant relations, a constant ratio between the depth of the ray and the unscaled estimation depth. So in most cases, let's take a look on this toy example. We see here that mu j and mu k are 2 times bigger in this, when the structure for motion is describing well by the intersection with the DTM. But in this case of the outlier, we see that 4 times bigger, deeper, and we can mark it as an outlier. We see it in an histogram where the x-axis represent the eta, which is the ratio between these two scales depth estimations, and we can see that most of them lay here around 37. So we can easily filter this kind of outliers. Another filter method is the slant angle condition. So between the ray and the normal, there is some angle, and as the angle approaches to 90 degrees, we assume that any small change in the estimated position will highly reflect the intersection point, which undermines the assumption that QT and QE lay in the same plane. So we would like to filter these cases and use more of the cases where the angle between the normal and the ray is small. So we can filter out features that with the angle that higher than 85, but it's a hyperparameter and could be changed. Patch curvature is another filter method where we calculate the curvature of each patch using its neighbor. So in this case, we can see that QE's neighbors are creating some high angle between the normal and the neighbors, So we probably would like to filter this kind of situation, this kind of features, because it also undermines the assumption that QE and QT lay on the same plane. In these cases, where the normal and the neighbor's angle is close to 90 degrees, we can be more sure that more convenient, or skewed, more sure that there are both QE and QT there on the same plane. So again, in this case, we'd like to filter this point. Residuals is our last filter, and in this case, I showed earlier this equation, the linear equation. So we can take a look at is an ax minus b, where x is the solution of the rotational error and scale. And if we will substitute the solution, we will get some residual. Now we can take a look at all the residuals and look for the STD, and the residuals that deviated from this STD will just filtered out. So let's take a look at the implementation. So as I said, we have the real position pose, which is our 1P1, but our navigation system produce only noisy estimations. But we see the same cliff in the same point in the image, and while raycasting from the true position will result in QT, in true position, raycasting from the estimated position resulted in QE. So we first identified and tracked features along the images, and then using triangulation, we can create our unscaled structure for motion. You can see it as the green dots here. The next step, we will raycast, ray trace, and now you can see it as the red dot, but in this 3D model, you can now see a bigger scale to the problem, although we see the formation in the 3D model. And our last step is to filter the outliers and solve this equation. And we can see that now the model is closer to the unscaled model, but now with the scale. After the ray tracing, we iterate this step of solving the equation and ray tracing until convergence. So let's take a look at the result. We validated our approach through extensive testing in both synthetic and realistic environments, but today we'll show the realistic simulations. We used AirSim simulation, which is based on Unreal Engine. And we can see here two scenarios. On the left, we see a top view scenario where the camera is pointing downwards with the pitch of minus 80 degrees. And on the right side, you see a more challenging environment with trees and cliffs, and the camera pitch is set to -40. So the setting is that the AirSim is produce DTM with a very high resolution of 1 meter, but we'd like to use a more conventional detailed level 2, which is about 25 to 30 meters resolution. So we sampled the DTM. And the flight on the left side is straight and level flight with 8 images, 30 meters spacing between frames. And then the challenging one is a straight flight with elevation, with 16 images, with the trees and cliffs. So to evaluate the performance, we generated some Gaussian noise, which we added to each of those trajectories, the flight trajectories. And we executed 13 different experiments where each experiment is both in rotational error or positional error. We performed Monte Carlo runs with an equal 500 at each experiment, and it was important for us to test 3 main properties of the algorithm. First is the position error orientation in each and orientation errors in each axis. Second, the mean value of the errors per axis and the correlation between the input and the output to confirm that the results were unbiased and statistically linearly independent, which is very important in any navigation system because we would like to use it as a substitute, as another sensor instead or alongside the lost GPS. And the algorithm performance, what's the number of iterations did it convert and the number of unsuccessful ones. We can measure the unsuccessful ones by measuring the divergence of the algorithm. Okay, so here we see the position error results. On the x-axis, we see an spatial error, or actually Euclidean error of up to 115 in the top view scene, and around 50 meters on the trees scene. And we can see that in both cases, the output is not related to the input error, which means that our algorithm is robust enough. And I will explain soon. And here we see the deviation from the solution. And we see that regarding the rotational error between 2 and 5 degrees, and I will explain and show what is this, what does it mean. Algorithm is managed to produce very good STD errors. And in the rotation case, we actually see here the input error as the geodesic distance, which is the distance along a sphere. And we measure it by degrees. So 4 or 5 degrees input in both cases. We also see a nice degradation to 0.1 or 0.6 on each axis. And we see once again that it's regarding the output is regardless the amount of input noise. Now we see the mean error, and we see that on each experiment, no matter that we increase the noise, the mean error still remained constant. Now we believe that this inherent error is due to the DTM inherent error, because there is a height approximation error alongside the DTM grid nodes. So it is reflected here. Now you may ask yourself, how come the the results are consistent along the experiments? How come we increase the error, the input error, but the output remains the same? So I will soon see how comes. Another important key, as I said, is the correlation of coefficient values, and we see that there is no correlation between the input and the output in both scenes. So we see now whether the increased error comes to play, and as we increase the error, we see that it takes more iterations until the algorithm converge, up to from 5 to 8 iterations in the slant angle view, the trees scene. And in the aspect of failures, we see that this is really changing the game, where in cases of very high error, our algorithm is not always managed to produce a good solution, or produce any solution actually. And it fails in some cases, and around 18% of the cases, challenging way. So we see here like around 95 maybe failures for 500 failures. This is a kind of ablation or a filter analysis where we'd like to see how well our algorithm performs. But moreover, it also compares our algorithm to previous work, because comparing the use of all filters comparing to none of them is basically the previous work, because in the previous work they didn't use any of the filters. So in this case, we see that while the number of iterations in typical version is not really reflected by the filter type. The amount of unsuccessful experiment is really influenced by the filters, and using all of them reduced half compared to none of them. It's interesting to see that using only the scale statistic have a slight improve over all of them, but we can now see that it comes with the cost of higher errors. And we can see that the adaptation error and position error are slightly higher. Not that high amount, but few times bigger than the use of all of the filters. So this is reinforced our assumption that using all of the filters is important to the success of the algorithm. So to conclude, we developed a new flexible and efficient algorithm for matching the unscaled structure for motion and solving the visual terrain-aided navigation problem. We have a new outlier rejection step, and which make the algorithm more robust and suitable for real-world data. And we proved that the algorithm is statistically independent, hence it's suitable for a navigating system. And thank you all. Thank you for the time.
Thank you, Dan, for this great presentation today. We will now accept questions from the audience. So as a reminder, you can submit your questions using the Q&A button in your viewer. So not the chat box, but the Q&A button down in your viewer. So feel free to send any questions in. We'll go ahead and wait here for a couple more minutes just to see if any questions roll through. No need to be shy. Feel free to send any in.
El estudiante.
¿Estás hablando con él ahora?
No, no. Y entro nada más para hacer números. A una charla.
Okay, we have a question here from the audience.
Okay, yes, let's see. So I will read it. What types of image features were used for image matching? Are they robust across seasons change? So we used SIF features, which are first of all, they are robust to usually to in our environment to scale. And yes, there should be also although it's seamless image, so it might be limited with the amount of season changes as rain and fog it can process through. So it's not about the features that are resilient to season, it's more about the camera. And the camera in this case is not resilient, but we can think of a setting that incorporate a more resilient to season and weather affection. I hope it answered your question.
Perfect. Any more questions from the audience? Please feel free to go ahead and send those in. Okay, it looks like we have no more questions, so we want to thank everyone for joining us for today's webinar. Oh, I'm sorry, it looks like we have one more question.
Yes. Okay, so I will read it out loud. How does this technical approach apply to degraded visual environments, cloud cover, smoke, etc.? Okay, so I kind of answered it earlier. It's not about the approach, it's about the sensor. In this case, we tested it with the CMOS alike because it's simulation, but it's in some cases like in fog or heavy rain, and where the features can't be detected. So this algorithm is basically won't be able to help in correcting the navigating system. So in these cases, I think that my other hat, where I work in other sky, where we actually developing this kind of sensor can help. So using maybe a thermal camera can come to play and come to the help of this kind of hard weather situation, and applying the thermal camera, which is another passive sensor, can help and to make this algorithm works in difficult and degraded visual environments, including cloud cover, smoke, etc. And to the second, I hope it answered. So to the second question, how critical would the DTM resolution be to the algorithm? Okay, so this is a good question. The algorithm do rely on the DTM performance, but as I showed earlier, there is one of our tests. So as a higher resolution will make the error be like degraded, not degraded as these solutions, because eventually we are limited by the space, and higher DTM resolution will improve the spacing and hence will improve our algorithm performance. And as the DTM will improve, the algorithm performance and correction will be tighter, will be more correct. So yeah, it's not as critical because we can still produce a nice and well output, a nice and well correction. But yes, we are limited. I mean, there is a correlation between how good the DTM is to our performance. Hope it answers the question.
Great. Well, thank you everyone for joining us for today's webinar, and thank you, Dan, for your presentation. We want to remind everyone that we will have a recording of this webinar available to the audience, and it will be posted to our website, YouTube, and other social media channels by this Friday, the 30th. So thanks again, and we look forward to having everyone back for a future ION webinar. Thank you.
Yeah.